All right, please, Francis.
Yeah, okay. So, yeah, thanks. So what I'll talk about is this recent preprint that I put up with Marco on the archive, which is called Brains on Torque Variety, Brain Quantization of Torque Poisson Varieties. So let me start by kind of giving kind of a big picture motivation for this project. And it basically comes from trying to construct categories of boundary conditions for generalized complex structures. So let me just recall, I guess everyone here probably already knows what a generalized complex structure is, but let me just recall. So a GC structure, it consists of a complex structure on T plus T star of M, which squares to -1, and it's integrable with respect to the Courant bracket. And the two kind of extreme examples that we know are symplectic structures, where the GC structure is given like this, by this formula. And the other extreme is complex structures. In this case, the GC structure has the following form. Okay, but for a general GC structure, what we're interested in is defining. So we want to define a category of kind of boundary conditions or GC brains. Something like this. So the two examples where this is actually known are these two extremes of a symplectic structure and a complex structure. So when we have a symplectic structure, this category of boundary conditions is called the A model. And the category is what's called the Fukaya category. And in this case, the objects are Lagrangian submanifolds equipped with some extra structure like a local system on it. And you have also these more general kind of conjectural brains that were discovered by Kapustin and Orlov that are supported on coisotropics. So brains supported on coisotropic submanifolds. So this is discovered by Kapustin and Orlov. Okay, so that's what we get in the symplectic case. In the complex case, then what we get is what's known as the B model. And in this case, this is the category, is the category of coherent sheaves. And you can think in this case, the objects are well, they're coherent sheaves, but you can kind of think of these as complex submanifolds equipped with a holomorphic bundle. That's kind of the objects in this case. Okay, so what about the other categories? What about the other GC structures? So what do other categories look like? So a clue for this is the following observation, which is that at least infinitesimally, the infinitesimal deformations of the A or the B model, and let me just focus on the B model. So the infinitesimal deformations of this category, they actually correspond to the infinitesimal deformations of the GC structure corresponding to the complex structure. In both cases, they're given by the following sum of cohomology groups. It consists of three terms. So one is global H0 of wedge 2 of T, tangent bundle, plus H1 of T and H2 of O. So these ones here, these correspond to the actual deformations of the complex structure. But the other ones on the outside, those correspond to deformations that kind of move you outside of the complex into more general GC. So these move you away from complex into GC. So these ones are some type of like gerb deformation, and these ones are the so-called non-commutative deformations. And these are the ones that I want to focus on. So if you have an element in here, this is a holomorphic bivector, and let's assume that it's integrable, so it defines.
Right. Francis, can I ask something? Yeah, so you keep saying to construct a category of boundary conditions. So I don't know, is this, I mean, are there some structural properties of the category that you want to recover? I mean, I don't know what you mean by boundary conditions for what? I guess you mean strings in a big sense, or is there, because I mean, the morphisms are the objects you want to go from here to there, right? So
Yeah,
is there
so
something?
I guess it would be some type of sigma model with a GC or a GK structure on the target.
And from the math point of view, is there like a list of desired properties that they want from this category? Or
so, well, what I was going to say is that the objects of these categories has been defined by Marco in his thesis, I think.
Okay.
But I guess like this here is kind of giving a clue that the deformations of the geometry of GC geometry, it's the same as the deformations of the B model.
Okay.
Okay,
so another way to put it is that you have these natural objects associated to GC structures defined by Marco, which are like boundary conditions for strings in, I mean, it's a mathematical replacement for boundary conditions for strings. And then you want to define the morphism.
Yeah, exactly.
Okay, thanks.
So I believe like the supersymmetric sigma models exist with like a GK target. And I think the problem is like there's no way of kind of reducing it to something like a Fukaya category of coherent sheaves. Yeah, but I guess I'm a little vague at the moment. It's just to serve as kind of motivation. Yeah, so what I was saying is that if you take a Poisson structure, so this is a holomorphic Poisson structure, then on the one hand, it should give you kind of a non-commutative deformation of the category of coherent sheaves. But on the other hand, it will give you a deformation of the GC structure I. And the way that this works is the following. So if you write the holomorphic Poisson structure like this, decompose it into real and imaginary parts, then you can define a GC structure with the following formula. So maybe one way of thinking about it is that what should be the category of branes associated to this GC structure? Well, it should be whatever category you get by deforming the category of coherent sheaves. But another way of thinking about it is that if we can construct the category of branes for this structure, so the category here, it will give a geometric approach to non-commutative geometry.
Sorry, can I ask a stupid question? So how does this non-commutative deformation of the category of quasi-coherent sheaves work? Is that, I mean, so if you have this holomorphic vector, then what do you do with the category then? Like, do you deform the morphism somehow, or?
So I don't really know about the details, but I think it's kind of through the Kontsevich formality.
Okay.
But this group here would be the Hochschild cohomology of the category.
Mm-hmm.
So that gives you at least the infinitesimal deformations. I think in order to actually deform it, you need to use like a formality theorem.
Okay, thank you.
Okay, so yeah, so the idea behind this project is to try to is that it would give kind of a geometric approach to these to non-commutative geometry, and I want to focus on kind of one kind of specific thing you can do, which is so instead of focusing on the entire category, I just want to focus on something you can do with a single object, which is the geometric quantization. So I just want to start by talking about, you're kind of reviewing the geometric quantization of Kähler manifolds. Okay, so how does this work? So let's start with M omega, an integral symplectic form. And let's choose, because it's integral, we can choose a pre-quantization. So it's a line bundle with a connection. And it has the property that the curvature is given exactly by this symplectic form. And now we want to pre-quantize, or we want to quantize this. So in order to do that, we have to choose a polarization. And so let's choose a complex polarization. So it's a complex structure. Let's call it a polarization. So it has to satisfy an equation, a compatibility with the symplectic form, which is the following. So this just says that that the form is of type 1,1, and let's also assume that the associated metric is positive. So we have a Kähler structure. Then what this says, I mean, what the prescription of quantization is then, is that we get a vector space, which is the kind of the sections of the line bundle that are flat with respect to the 0,1 component of the connection. So in other words, it's the holomorphic sections of the line bundle. So this is the quantization. Okay, so when we construct this quantization, the form, the complex structure I is kind of playing an auxiliary role. You can think of that it's kind of allowing us to view L as an element of the category of coherent sheaves, but it's not encoded in the quantization. And, you know, if you're in a really good situation, then you might even have invariance under change of polarization, so that if you change the polarization, the quantization will not change. So the quantization, it does not encode the complex structure. But the way to actually encode the complex structure is something that's well known in algebraic geometry, which is what you're supposed to do is you quantize not just omega, but all of the integer multiples. And when you do this, you put them together inside of in a big direct sum. And this thing now, it has the structure of an algebra. You can multiply elements. So this is the homogeneous coordinate ring. And the Kodaira embedding theorem it tells you that that you can just from this algebra you can encode just from this algebraic structure you can reconstruct the Kähler variety. So it completely encodes. This encodes I. You can kind of think that the complex structure is encoded in the product on A. And so one way of thinking about what we want to do is we can imagine deforming I as a polarization to kind of a generalized complex polarization by turning on a Poisson structure. And what this will do is it will deform the algebra. It won't deform the vector spaces, but it will deform the product. So it deforms to some algebra, which is now non-commutative. And this is the deformation quantization of the Poisson structure. Does this make sense so far? So I want to kind of rephrase this now. I want to rephrase this now, just kind of completely in terms of well, first of all, rephrase the homogeneous coordinate ring completely in terms of the category of coherent sheaves, so that you can kind of see how this algebra can be deformed by turning on a Poisson structure and deforming the category. So let's kind of view this from the perspective of the category of branes. So the homogeneous coordinate ring, again, it's this direct sum of global holomorphic sections of the tensor products of the line bundle, but we can write it in the following way. As homomorphisms in the category of coherent sheaves from the trivial bundle to another bundle, which I'll call phi k of O. So here, O is the trivial bundle, and phi, it's going to be a functor from this category to itself. And what it does is it takes any coherent sheaf and it just tensors it with L. So that this thing here is really equal to L to the kth power. Okay, and then you can define the product. If you have, say, AK tensor BR, the way that you define the product, well, BR is going from O to L to the R, and AK is going from O to L to the K. So what you can do is apply phi R times to AK, so that it goes now from LR to LK plus R, and then you compose it with BR. Okay, so this allows you to kind of see this algebra kind of internal to the category of branes in the B model. Okay, so now if we want to turn on the deformation, so we would deform this category, say to this category here, and then if we want to kind of deform this algebra, we'd also try to deform both O and this this functor. So let's just try to do this. So as I was saying earlier, that in Marco's thesis, or it's either his thesis or his annals paper, maybe both, is that the objects of this category that we want to define, these have been defined. So there's a general definition, which I'm not going to give. I'm just going to give a simplified definition that will work for the case at hand. So what I'm going to call a brane on this GC structure corresponding to this holomorphic Poisson structure. Remember, sigma is this. So a brane is defined to be a unitary line bundle L nabla, such that the curvature satisfies the following equation, which is that Fi plus IF plus FQF is equal to 0. Okay. So this should be a familiar equation. Notice that if Q is 0, then you just get the 1-1 condition. It's exactly the same equation that we had earlier in defining the geometric quantization. So it's this equation is getting deformed when we turn on the Poisson structure. So there's always a canonical space-filling brane. Well, let me just say there's a canonical brane, which is given by the trivial bundle with the trivial flat connection, right? Because in this case, the curvature is 0, and that's trivially a solution to this equation. So we always have at least this object. And in Marco's paper on branes on Poisson varieties, he showed how you can produce more examples of these. So what he showed is the following. So if this unitary line bundle, let me say unitary holomorphic line bundle L nabla, say the one that we were considering a moment ago, if this thing admits a Poisson module structure, so a Poisson module structure, it's a lift of the Poisson structure sigma to the total space of L. So if this bundle admits a Poisson module structure, then the functor phi, it deforms to some other kind of functor. Well, we can't really say it's a functor, but it's at least gives you a map from that takes a brane and it gives you another brane. So this is the way that you do this is this kind of flow construction, which is so important in GK geometry. So for example, if you take T and you plug in O, because O is a solution to this equation, so you can apply T to it and it will spit out a brane, so it will spit out L, but with kind of a deformed connection. Yeah.
Sorry, Francis, I have a very basic question. So in this definition of branes, so I guess like nabla is, I guess like not a holomorphic connection. I mean, that's the point, because otherwise, okay, so it's a holomorphic line bundle just without, but nabla is not a holomorphic connection.
It does not need to be holomorphic. Notice that here, if you just took a unitary line bundle with a Hermitian connection, and its curvature satisfied this equation,
Right.
then it would automatically define a holomorphic structure on L.
Right.
By taking the 0, 1 part. So you can kind of think that you can think of the objects in that way. It's a unitary bundle with a connection such that the curvature satisfies this equation. When the GC structure is complex, it automatically becomes a holomorphic line bundle. But in this case, it's something more complicated. It's not, because it's not 1, 1. The curvature is not 1, 1 with respect to either complex structure.
Yeah. Okay. Yeah. Thank you.
Okay, so given so
Can you recall what is a Poisson modular structure?
yeah, sure. So it's just how to say it. You could imagine that it's, let's say, M sigma is a Poisson manifold, and L is a line bundle. One way of thinking about a Poisson module structure is kind of a linear Poisson structure on the total space of L. So it's invariant with respect to the rescaling action, such that if you project it, it gives you sigma. So in particular, that means that this allows you to bracket sections, that allows you to bracket functions on M with sections of L. So it gives you, so this produces like a bracket of like functions on M times sections of L to L. Because you can imagine that you kind of pull them back, you pull a function back to L, and then you use the Poisson bracket on L. Does that make sense?
Yep. Can you go one moment to the previous slide? Yeah, thanks.
So what I wanted to say is that now, like we kind of know how to deform this trivial bundle. It kind of automatically deforms to a brane, and this autoequivalence, it kind of also deforms. And so we should get out of this a deformed algebra. Just by kind of following the same rule. The problem with this, though, maybe I'll put it in red, is that we don't actually have a category. We don't know how to compute homomorphisms in the category of branes. So we're stuck. Okay, but yeah, so what I wanted to kind of at least kind of the point that I wanted to get across is that if you having this category of branes, it should be kind of closely related to non-commutative geometry. Kind of in particular, you could deform the non-commutative homogeneous coordinate ring to get a kind of a deformation quantization. And if we could construct this category, we would kind of get a geometric approach to constructing these algebras. Okay, so what the paper is about, or what this project is that we're trying to develop a new approach to constructing the category of branes. And our approach, it kind of converts the problem into something involving symplectic geometry. So we'll kind of give a new approach, which doesn't yet work kind of in full generality. But the problems now are of a different nature. It's more about understanding the A model of a symplectic manifold. Yeah, and so in our paper, we focus on deforming the homogeneous coordinate ring of a toric Poisson variety. And I should say this kind of idea of getting a geometric approach to non-commutative geometry using GC geometry, I think that this goes back to probably almost the beginning of generalized geometry. Definitely in Marco's paper on branes on Poisson varieties, he had something like this in mind. And the problem is always, the problem has been that the inability of defining the homomorphisms. So this project here is kind of the first little bit of progress towards doing this. So in order to explain this, I want to go to back to geometric quantization. So the approach that I gave here, it was kind of the B model approach using the category of coherent sheaves. So I want to give now kind of an A model approach. And the idea here, and this is something that it goes back to the work of Donaldson, and it's definitely what I was thinking is kind of related to what I was doing in my thesis, but not exactly phrased in this way. But the idea is to encode Kähler geometry mi omega as a pair of A branes in a symplectic manifold, which is the cotangent bundle, just the real cotangent bundle of M. So this is a canonically defined symplectic manifold that we have for any manifold. And we want to encode the Kähler geometry as a pair of branes. So let me draw the cotangent bundle. Here's M, and here's T star of M. Here's the kind of the fibers of the projection. So what are the two branes? So the first is a Lagrangian brane. Which I'll call L, and it's given by the zero section in the cotangent bundle equipped with the trivial local system. So it's something like this. The second is a space filling brane. So this is one of these more general branes that are supposed to be in the A model, but which symplectic geometers have not really incorporated into the Fukaya category so far. So a space filling brane. And what this is given by, so let me just describe it first, and then I'll give the definition of a space filling brane. So I'm going to call it B. And it's given by a line bundle on the total space of the cotangent bundle. So I'll call it U, and equipped with a connection, which I'll call nabla hat. So the line bundle is going to be given by the pullback of our pre-quantum line bundle L to the total space. So here's the projection map pi. And the connection, nabla hat, it's going to be, well, we take the pullback of the connection on the base, but we want to modify it. We modify it by adding a one form, which I'll write like this. So let me just kind of explain. So the cotangent bundle, it's a real symplectic manifold with a symplectic structure. But the fact that I have that M is actually complex means that the cotangent bundle can also be thought of as a holomorphic symplectic manifold. And so it has a holomorphic symplectic form. This comes from the complex structure I. And this thing, it has a primitive, a holomorphic primitive, which is alpha naught. So I'm going to take D of alpha naught. Sorry, D of alpha naught is omega. It's the kind of the canonical primitive. And so what we're adding on is not all of alpha naught, but just the real part. So this gives you kind of a deformation of the pullback of the connection. So if I draw this brane, it's kind of living on the entire space. Okay, so let me just say, what is a space filling brane? So U nabla hat is a space-filling brain if, so let's call the curvature F. Let's say, so F is going to be I over 2 pi nabla hat. So if this thing is such that F plus I omega naught is a holomorphic symplectic. Does this make sense? So the condition is that if we take the curvature of our line bundle and then add it to I times the canonical symplectic form on the real cotangent bundle, this thing gives you a complex form, and this thing, it needs to be holomorphic symplectic for some complex structure, which it will define just by the nature of it being 2-0.
Sorry, Francis, can you just remind me how big omega naught is related to little omega naught?
Yeah, so the imaginary part of big omega naught is little omega naught.
And okay. So they are just,
Yeah, so let's look at this example. So in our case, F is going to be the pullback of omega, right? Because omega was the curvature of this nabla, but then plus the real part of d alpha naught, which is the real part of omega naught. So if we take F plus I omega naught, what we get is pi star of omega plus real part of omega naught plus I times the imaginary part of omega naught. So that's omega naught. This is the original holomorphic symplectic structure, but deformed by adding the pullback of the Kähler structure. So this thing, this symplectic form here, it's not, it's kind of deforming. It's not the canonical symplectic structure. It's the so-called twisted cotangent bundle. In the kind of the language of our paper, it's the kind of it's kind of these non-trivial Morita self-equivalences. Does this make sense?
Yeah, thank you.
And
what you call little omega naught, is it defined by the imaginary part of big omega naught, or is something else that you had before?
Well, no, that's what it is. Yeah, because the cotangent bundle, it has a canonical real symplectic form, which is little
but
omega
this
naught.
is your definition, right? It's not something that appeared before. It's just before you had the cotangent of M with the complexified, with the natural holomorphic symplectic structure, right?
Let me put it this way: like if you have a real manifold, its cotangent bundle has a symplectic form, canonically defined, which is little omega naught. If you have a complex manifold, it has a cotangent bundle, which is a holomorphic symplectic manifold, which is canonically defined. And so how are the two related? How is the real symplectic structure related to the holomorphic one?
Okay.
Well, if you take the imaginary part of the holomorphic one, you get the real one.
Okay.
Yeah.
So is this your definition of a space-filling brain? Is it the same as in Bukov-Witten and Kapustin-Orlov, or is different?
Yeah, it's the same thing. This is exactly one of these space-filling brains of Kapustin-Orlov. It also coincides with the definition of a GC brain that Marco gives. So I think maybe this was one of the clues that the definition was kind of in the right direction, that the natural definition of a brane for a GC manifold, if you specialize it to complex or symplectic, it actually doesn't give you just, well, if you specialize it to like Lagrangian, if you specialize the definition to symplectic manifold, it doesn't just give you Lagrangian, it gives you also the coisotropics. They kind of naturally pop out of the definition. So the idea is that we encode the Kähler structure in these two branes, the Lagrangian one and the space filling, and they actually you can recover the Kähler structure from those two branes. Well, let me just kind of note it, is that if you intersect the intersection, it recovers the Kähler structure, in the sense that if you take this U nabla hat and you pull it back to L, you get L nabla, the original pre-quantization of the Kähler structure. Okay, so the quantization then is defined as a space of Homs in the A model. So we define Q to be homomorphisms in the A model of little omega between L and B. So this is closely related to something that came out of the work of Witten that he has been doing with Gukov and then more recently Gaiotto, which is kind of a new approach to geometric quantization, where what they say is that you take, if you have a symplectic manifold, what you're supposed to do is complexify it. So kind of embedded inside of a holomorphic symplectic manifold of twice the dimension, such that it's kind of embedded in the same way as we have here, where it's Lagrangian for the imaginary part. So in this kind of picture, you get the same thing. You have a Lagrangian brane and a space filling brane, and they say that the geometric quantization, it should be given in this way. So in this project, we really took inspiration from this approach. So the difficulty with this, with doing this, is what I alluded to earlier, that symplectic geometers, they don't really know how to deal with coisotropic branes. The Fukaya category is usually done just with Lagrangians.
Can you clarify one thing? So what is the role of the complex structure in your picture?
The complex structure?
Yeah,
Sorry?
so I mean, what is it? So what you mean, cotangent of n, I guess, is the dual of the tangent 1, 0 of n, right? With respect to the complex structure of phi. Am I correct?
Yeah, so the omega naught kind of goes into the complex structure goes into defining this omega naught.
Okay.
Yeah, it's sort of the space filling brane B. It kind of encodes the Kähler class as well as the complex structure, and this L, it kind of encodes the metric, the specific representative. So if you kind of deform L, it will change the Kähler form by dd bar of by a function.
Okay.
Is that okay?
Yeah, and what is the relation between these two pictures? Because I mean, you said that you could realize the geometric quantization in the B model by means of the construction that you had before, and now you have this other picture, which is like the A model side. And
yeah,
how are these related? Is there anything?
Yeah, so I claim that it should be the same thing. This should recover the global sections of L. So there isn't really a general way to compute this, but we have kind of a proposal that seems to work for our purposes. So I'll just say, what is the proposal to compute this? It's based on holomorphic geometric quantization. So what
But
we do,
I'm a bit confused. So if I literally apply the definition of Markov for brains, thinking of the Keller structure as a generalized Keller structure in the canonical way, what are the brains? The second ones, or
do you mean if you start with a Keller structure?
yeah, and I think of it as generalized Keller, then I would get what you call the B picture or the A picture.
Right. So we're not using the A model of the Keller structure of omega. We're viewing omega as the curvature of a line bundle. So it's a brane in the category of coherent sheaves. It's a holomorphic line bundle on the complex manifold I, like MI.
Okay, so you just have okay. So you're thinking of the complex structure as the GCS, and then your omega is an auxiliary object.
Exactly. So what we're doing is that we're taking this object and we're kind of encoding it instead of, so we start with an object in the B model, but we kind of encode it in as an object in the A model, well, as a pair of objects in the A model of an auxiliary space, which is the cotangent bundle.
Okay, yes, I'm a bit confused from this difference between A and B, because if I give you a GCS, you're supposed to canonically construct a category. And so I'm a bit confused about what distinguishes A and B models in this picture.
So the strategy that I'm going to explain later is that the idea is that we're going to, starting with a generalized complex structure, what we want to do is we want to find a way of taking the branes for this GC structure and convert them into branes in an A model of an associated symplectic structure. So it's the idea is to kind of convert everything into the A model, where we don't necessarily know how to do all the calculations, but it's kind of somewhat progress because we can do some calculations now. I think maybe it will become a little bit clearer in a minute. So yeah, so what I wanted to explain is how do we actually compute this isomorphism? So how do we actually construct the space of homomorphisms? And our proposal is based off of, it's kind of based on the holomorphic geometric quantization. So it has the following steps. First of all, we construct a holomorphic pre-quantization of this space-filling brane B. So we take U, but instead of having nabla hat, we take D, which is nabla hat plus, if you look here, we added the real part of alpha. So now we'll add the imaginary part of alpha naught. So in other words, this is the pullback of L, and the connection is the pullback of nabla minus 2 pi I alpha naught. The interesting thing about this connection is that now the curvature is exactly this thing, which is holomorphic. So D actually gives us a holomorphic pre-quantization of this holomorphic symplectic structure. Okay, so that's the first thing. The next step is that we have to choose a holomorphic polarization. Of this holomorphic symplectic structure. And what we'll take is the fibers of the projection.
Sorry, Francis, can I interrupt again? Yes. So, yes, so to get the picture. So, you're calculating, you're interpreting these sections of the line bundle as ohms in your category for the complex structure for the GCS associated to some ordinary complex structure. And you know how to calculate that. We know how to calculate that. And now what you're saying is that out of this, I'm going to construct an auxiliary holomorphic symplectic manifold, do some complicated calculation and recover these ohms that we know, with the hope that if I have a more complicated GCS at the beginning, I can also calculate this more complicated holomorphic symplectic manifold, do this construction, and define the ohms via this construction. Is that the picture?
Yeah, exactly. And
okay, thanks.
And this picture here that I'm doing here, we can actually deform it. Whereas the other one, when we tried to deform, we got blocked. We didn't know how to calculate morphisms. This one, it will deform.
Okay, but this other holomorphic symplectic manifold is an auxiliary object that you are going to associate by GCS. And hopefully for more complicated GCS than just complex structure, it will give you the right answer.
Exactly.
Thanks.
Exactly. Yeah. Okay, so so we have the holomorphic prequantization of B. So we equipped U with actually a holomorphic connection whose curvature is this holomorphic symplectic structure. We take now a polarization, so we foliate this holomorphic symplectic manifold with holomorphic Lagrangian submanifolds, which are the fibers of this projection. And then to define the space of homomorphisms, what we say is that we take it to be the holomorphic kind of flat sections along the leaves, along the fibers, which intersect L. So the idea is that I have this kind of foliation, and I'm just looking at the space of sections that are flat in those vertical directions. So they're constant. And I only want to look at the leaves that actually intersect L. In this specific example, every fiber intersects the zero section. So I'm just looking at the sections that are constant in the vertical direction. And so when you do this, like sections of U that are constant in the vertical direction, that exactly recovers the holomorphic sections of L. So that's how we view the geometric quantization from the A model perspective. So what about the homogeneous coordinate ring? So this was the algebra that we constructed by quantizing not just omega, but all of the integral multiples. So we could similarly construct all of these vector spaces in the same way, but where does the product come from? So that comes from the fact that on the cotangent bundle, you have the fiber-wise addition map. You can add the vectors and the fibers. So this addition, it makes the cotangent bundle into a symplectic groupoid. So this addition map, it's actually a Lagrangian relation between T star cross T star to T star. And what this does on the categorical level is it endows the A model with a tensor product. So you can take branes and you can tensor them together, kind of just by adding them up. And if you have morphisms, you can also add those up, kind of tensor them together. So for this A model, so remember we had this brane L, which was the zero section, and the zero section, if you add it to anything, it doesn't do anything. So L is the tensor product unit for the tensor product. And so what that means in particular is that if you tensor L with itself, you just get L again. On the other hand, what happens if you take the space filling brane and you tensor it with itself? You can do it kind of however many times you want. You could just keep tensoring it. So this will encode the rescalings of omega. Okay, so what that means is that the algebra, it's going to be given by the direct sum of the spaces of homomorphisms in the A model from L to all the higher tensor powers of B. And then
can you say more explicitly what is this B star, B star?
Yeah, okay, so if you have two branes, in this case, they're going to be, say, space filling branes. So they're going to be kind of supported on the entire space, and they're going to have line bundles on them with connections. And you want to tensor them together. And the way that it works is that the direct sum, what I was saying just before, you can think of this as a Lagrangian relation between T star cross T star to T star of M. This is the direct sum. It's a Lagrangian relation. So the direct sum, kind of the product on the groupoid structure, it's encoded itself as a brane inside of T star cross T star cross T star. And so you can compose, you can tensor the branes together by composing Lagrangian relations. So the fact that you have these two, when you have a brane, you can think of that as, well, not a Lagrangian relation, but kind of some type of relation going from a point into B cross B, sorry, into T star cross T star. So you kind of compose these together and it will give you the tensor product. Does this kind of make sense?
Okay.
It's let me just say, in the paper, it's explained in more detail in section 2.7. so what you can do kind of more explicitly is you can take you would take the kind of the fiber product of B1 with B2, and then you would kind of push it forward into M, and that will be supported on some submanifold. And same thing with the, so the way that you would so doing this on the level of just the on the submanifold, it's not doing anything because it's supported on the entire space. But you can look at what happens on the line bundles. So you have kind of U1, say you have this one has the line bundle U1 with connection nabla1, and this one is U2 with connection nabla2. Then you can kind of take the product of these things, of these two line bundles with connection, which will be supported on the product. Then you can kind of restrict it to the fiber product. So you take this thing and you restrict it to T star M fiber over M with T star of M. Okay, so this fiber product is a coisotropic inside of T star of M cross T star of M, and the map, the addition map, is the symplectic reduction. Because these and because these connections, they were themselves like pre-quantizing, well, they were kind of related to pre-quantizations of symplectic forms. What you'll see is that they're going to be flat in the directions that you're trying to quotient out. So you can also kind of push forward the line bundles in that way.
Thanks.
Yeah. If you do it in this case, you'll see that you'll just get the tensor product of the line bundles, just because the addition structure is pretty simple. But this kind of explains, from this perspective, kind of conceptually, where does the product come from? Because what you can do, say you have HOM from L to B N and HOM from L to B K, well, you can apply the tensor product to the maps, and it will send you to a HOM from L tensor L to B to the N tensor B to the K. But this is just isomorphic to, well, this thing is just HOM, this thing is just L, and then this thing is B of N plus K. So in this perspective, the product on the algebra, it comes from the tensor product on the category. Does that make sense? Okay, so that's how you can view the homogeneous coordinate ring from this perspective. So now I want to kind of explain what you would try to do in general. So generalized complex branes, A model approach. So this will kind of be a kind of schematic, and then I'll try to explain how we implement it in the case of toric Poisson structures. But this kind of idea, it should work more generally. So the question is, so given GC branes B1 and B2 for some GC structure I, how can we describe the homomorphisms between them. Okay, so this has several steps, and if you check what happens in the case of a complex structure, it will reproduce what we just discussed here. Okay, so the first thing is that a GC structure say I, it has an underlying real Poisson structure. If you just write out kind of as a 2x2 matrix the GC structure, it'll have some terms here, here, and here, but this term right here, it's always well defined, and it's a real Poisson structure. Okay, so we have a Poisson structure, and this we can integrate it to a symplectic groupoid. So Q may be integrated to a possibly local symplectic groupoid So what is this? So this is, it's a symplectic manifold that you can kind of canonically associate to any Poisson manifold. So it's going to be kind of some big space. So it's going to be a symplectic manifold, which has twice the dimension as M. So it's going to be some big symplectic manifold, and it's equipped with these maps, S and T to M. And you can think of these maps that they're kind of desingularizing the Poisson structure, in the sense that Poisson structure in general, it kind of gives a complicated decomposition of the manifold into these symplectic leaves. But all of those, you can kind of resolve them in terms of a big symplectic manifold and a map. So these maps, they have the property that, for example, if you take T and you try to push forward the inverse of omega, it gives you pi. But G actually has even more structure than just these maps. It has a kind of a partial multiplication. So you can think of a point inside of G is it corresponds to a type of path inside of M. It's a special type of Hamiltonian path. It's kind of a flow of a Hamiltonian vector field. And so you can kind of think of this as being kind of like a moduli space of special types of Hamiltonian paths. Okay, so as a result, you get to this space which has this kind of partial multiplication. What that means is that you get kind of the multiplication. It's kind of from the perspective of symplectic geometry, it gives you a Lagrangian relation between G times G to G. And the reason that this is significant is that this structure, so we have this symplectic groupoid, which is sort of canonically associated to our Poisson manifold. So we can take its A model. And the fact that we have this multiplication structure, it means that the A model of G omega has a monoidal structure. With unit object given by the so-called identity bisection. So that's a submanifold inside L, which is kind of the constant path. It's the submanifold of all constant paths. So what we were seeing before with the cotangent bundle, that was a special case. So in this case, the Poisson structure is 0, so the Hamiltonian paths don't let you move around. So that's why you get kind of just, in this case, just a vector bundle with the fiberwise addition. And this identity bisection in this case is given by the 0 section. Okay, so this this A model on the groupoid, it turns out to be very closely related to the original GC structure. So this is something that was observed first by Marius Kreinek. In one of his papers, he observed that if you combine these two maps, T and S, which are like the source and the target of the path, that gives you a map from G omega to M cross M. And if you equip M cross M with kind of the product of the GC structure and its transpose, well, now you have a map between a symplectic manifold and a GC manifold, and a symplectic manifold is GC. What he showed is that this map is actually generalized holomorphic. So the upshot of this is that given GC branes, BI and BJ on the GC manifold, we can pull them back to obtain an A brane. Because the nice thing about generalized holomorphic maps is that they allow you to pull back branes. So we get to this brane Bij, which is the pullback by this map of Bi times Bj. And so our proposal for defining the HOMs in the category is that we would define the homomorphisms from Bj to Bi as the homomorphisms in the A model of the groupoid from this identity, this monodal unit, to Bij. And then the composition defined using the tensor product structure.
Can you see what is in the definition of the generalized composite structure and the product? So the second GCS is what is I tau? What do you write there?
It's like the transpose.
So therefore Bj should be modified as well, right? When you define Bij, you should modify Bj in some sense.
Yeah, exactly.
Okay, this is not what you wrote, right? You literally took the product, but I guess it has to do with the fact that you want an adjoint.
It should be something like that.
Okay, yeah.
It would be like if you had like line bundles Li and Lj, you'd want to get something like Li tensor Lj dual, something like that. Yeah.
And sorry, I just a very basic question. So this Kreinek result you mentioned, I mean, this TS, it is just like a smooth map of smooth manifolds.
Mm-hmm.
But then what does it mean exactly for it to be generalized holomorphic?
Right. So it means that you can take the graph of TS inside of G times M with the GC structure like this,
Okay.
And this submanifold, it has to be equipped with the structure of a brane.
Oh,
So it has living on it a line bundle with connection, which satisfies some equations similar to like this one that I wrote here.
I see.
And so that's what you need to pull things back. It's like this similar to what I kind of tried and failed to explain about the tensor product. It's again like composition of relations allows you to kind of push things forward and pull them back. So this is kind of like a schematic picture of how it would work. And the problem again is that like these things, they will in general be quite, like they won't be Lagrangian. So again, we have this problem of how do we actually compute these Helm spaces. And I mean, even if we didn't have this problem, working in the Fukai categories is more complicated than kind of as I kind of indicated here. So to make this work in general would take some work. Yeah, but kind of hopeful. And yeah, so we have a case where we can make everything work. So that's the case of toric Poisson structures. Are there any questions actually so far about this kind of general picture? Okay, so yeah, I'll just explain now what happens in this specific example of toric Poisson structures. So let's start with a toric Kähler structure. So we have a kind of a compact torus, which is living inside of a complex torus, and this is acting on our Kähler manifold such that the action of C star preserves the complex structure, and the action of the compact torus is Hamiltonian for this symplectic form with the moment map. Something like that. Okay, so what do we get from this? So first of all, we get from this, well, just from the fact that we have the C star to the N action on the complex manifold, we get a lift of the C star N action to a Hamiltonian act, to a holomorphic Hamiltonian action of C star to the N on the holomorphic cotangent bundle, which has a moment map. Like this. And this is actually quite simple. We just, the infinitesimal action well, let me just leave it at this. Okay, so that's the first thing we get. The second thing is that if we now choose a pre-quantization of M omega, then we get an equivariant structure on it. So we get an equivariant pre-quantization So by that, I mean that we have a lift of the action. Let's say the action was called rho. We now will get a lift of the action to the automorphisms of the line bundle. Okay. So now we want to deform the picture with a Poisson structure. And so for that, we're going to choose a so-called R matrix, which is really just an antisymmetric matrix. So here R to the n is the Lie algebra of S1 to the n. And what this does is it defines a holomorphic Poisson structure on M using the C-star action. So this defines holomorphic Poisson structure sigma C, which is just obtained by pushing forward the R matrix using the action. And we also get a Poisson module structure on L, which I'll call sigma C hat, which is just obtained by pushing forward with this lift here, the R matrix. Okay, so that gives us, oh, let me just say, I chose my R matrix here to be real. That's kind of a restriction. You could choose it to be complex. And in fact, in the paper, we do take it to be complex. I'm just choosing it real here because it makes some statements less confusing to state. So just for simplicity, but it's not an essential feature. So now what we have from this is we have all of the ingredients to deform. So remember, a holomorphic Poisson structure, it allows us to deform I into GC. So let's call this I sub T, which will be this GC structure, where sigma C is written as maybe of this form. Okay, so that's a deformation of the GC structure. But also, if you remember Mariko's theorem, which is that in order to deform the L into a brane, we need to choose a structure of a Poisson module on the line bundle, and that's exactly what we have here. So we get a deformation of of L, or the operation of tensoring with L, to this kind of endo functor T sub T using the flow construction.
Sorry, can you recall again what is sigma C, this Poisson structure associated to the R matrix? How do you define it?
Right, so rho is the action. So infinitesimally, it's a map from the Lie algebra, which is say Rn, into the holomorphic tangent vectors, right? Because it's gives a holomorphic action. The R matrix is something in wedge 2, R to the n. And so if we push it forward, it's going to be an element of wedge 2 of T. And the Jacobi identity is just automatically satisfied.
Okay, thanks.
Okay, so let's kind of go through the prescription for what I was just describing. So first we should say, so we got the GC structure. What about this symplectic groupoid? So this symplectic, the symplectic groupoid thanks to some work of Weinstein and Ping-Shu, the symplectic groupoid of sigma C is very simple to describe. Let me call it G sub T omega sub T as for the family. Let me just call it just G omega. It's actually going to be a deformation of the cotangent bundle. And the underlying symplectic manifold is just the regular real cotangent bundle. What this means is that, in fact, the underlying A model is unchanged. So you see, when you turn on the deformation, it kind of will deform the groupoid. The A model, which we had on the cotangent bundle, it will remain. What changes when we define the symplectic groupoid is the structure maps. So the structure maps of the groupoid get deformed. So remember, we had the cotangent bundle, which just had a single map, which was the projection, which had these fibers. When we turn on this R matrix, this single map is going to split now into two maps, T and S. So it's going to kind of split, and the product is also, instead of being addition, it's also going to be deformed. So let me just give the source, this target and source. So the target of Z, it's equal to a deformation of the projection map given by the following formula. So you see, we're using, oops, let me. The source one is the same thing with a minus sign. So instead of just having the projection, look what's coming into. There's kind of, we're using both this R matrix C and the moment map, the holomorphic moment map, to kind of deform the projection kind of in two directions with like either plus or minus. So what this means, so there's a similar formula which kind of deforms the addition in a similar way. So what the upshot of this is that we're deforming the groupoid structure, so that's going to deform the monoidal structure. So the monoidal structure on the A model is deformed. Okay.
Sorry, can you say what is the meaning of this exponential map? Can you clarify that?
Sorry?
You have the exponential of a half of C applied to G0 set. So G0 set is an element in Cn, right? Then you apply C. So
Right.
then you get to.
Yeah, so we can think of it in this way. So let's call the Lie algebra, say T. The moment map, it goes to T dual complexified. C is an element of wedge to T. So in particular, it can define a map from TC to T. And so that means that if I combine C and J together, it gives me a map from TM to T. And now T acts on the cotangent bundle through the exponential, through the C star action. So I can exponentiate it. So when I exponentiate it like this, it now gives me a map into the group. And then that acts on T star of M, or it acts on M. So the kind of the picture is that we have some cotangent vector. It's living above, so it's, let's say Z, it's living above a point pi of Z. And instead of just projecting to here, we're gonna plug Z into CJ0 and exponentiate it to get an element of the torus, this thing here, and then we're gonna apply it to kind of move our point around. Like that.
Okay, thanks.
Okay, so let's look at, let's look at again the list of things that we're doing. So we got the groupoid, we got the A model on it, and now we want to produce these A branes by pulling back the branes on the base. And we get the brane on the base by doing the flow construction, right? Because that's what we needed. We have the Poisson module structure, and so we can get these branes on the base. So let's say let.
Can you say again what is the source? The source is just with a minus, so it's still flowing the other direction.
Yeah, exactly.
Okay, thanks.
So let's call BI the result of applying T I times to O, which is a GC brane for I sigma. Is that what I was calling it? Okay, so it's computed using flow construction from the Marcos paper on branes on Poisson varieties. Then we can pull it back to get an A brane on the cotangent bundle, and the result is that it actually gives us the brane that we had before. So this is the brane constructed earlier. So
can you say again what is TIG? TI of what is this? TI is, I don't understand. So TI of okay. So you play TI.
Right. So I'm saying because we had the line, the pre-quantum line bundle with the Poisson module structure, we can apply Marcos theorem, and that gives us one of these GC branes for the Poisson structure. This is just applying this flow construction that we use in GK geometry all the time. So that's what I'm calling BI. And then if we want to get a brane in the A model of our groupoid, we should take this brane and say multiply it with combine it with another brane, which is just going to be the trivial one. And then we pull that back using this combination of the target and the source map. And that will give us an A brane in the groupoid, which is the cotangent bundle. And the theorem is that this is actually exactly the brane that we had in the first place. The one that we had constructed over here. So the groupoid doesn't change when the symplectic manifold underlying the groupoid, it doesn't change when we turn on the Poisson structure, and the brane doesn't change when we turn on the Poisson structure. All that changes is the tensor product. So just as a remark, is that when C is not real, this is not true. So it changes to something else, but it's not, it's very close. It doesn't really cause any issues. I just don't want to go through the details of that. So at least in this case, the upshot of that is that this space of homomorphisms is unchanged through the deformations. But the product is deformed since the monoidal product gets deformed. So okay, so let me explain what happens in this case.
So is I in the statement of the theorem the same as K, or is K?
Yeah, exactly.
Thanks.
Sorry. Okay, so let me explain what happens in this case. How do we actually construct the algebra? So first of all, this BK, remember it underlying it, this kind of correspond, how can I say, this thing, underlying it, we have a holomorphic symplectic structure on the cotangent bundle, which is not the standard holomorphic structure, it's this deformed one. So underlying this, we get this kind of twisted cotangent bundle, a twisted holomorphic cotangent bundle. But let me just write it now as Zi omega I. Let me write it just as Zk omega K. So this is the holomorphic symplectic structure that's underlying the brane. And it also has this prequantization. Remember, we had this holomorphic prequantization. I'm going to call that UK dk. So that's kind of the geometry underlying the brane. The thing that the tensor product, the thing that you get from the tensor product is a way of combining these ZKs for different values of K. So the tensor product, what it leads to is kind of a Lagrangian relation like this between these different spaces. It's not the usual addition, it's been deformed. And it also is equipped with kind of whatever this relation is, it kind of lifts to the level of the holomorphic prequantizations. And so the tensor product on the level of line bundles, it's in the tensor product is also kind of for these UK dk, we get a cocycle. And by cocycle, what I mean is that we get a map from UK kind of box UJ to UK R, UK plus R. And this thing, it's also constructed out of the R matrix and the moment maps in a similar way. Let me just give the formula. It might not completely make sense, but if I have kind of some element F and G in here, and I want to get an element in here, the way that you're supposed to take to multiply them is sort of according to this formula. So you first use the moment map applied to the two base points x and y, and you plug them into the R matrix, and that gives you a complex number, which you can exponentiate. So that gives you like a prefactor. And then this is multiplying a tensor product of f and g, but they're kind of, so just as the deformation, it involved kind of moving these points around like in this way, according to this rule, we're going to do the same thing to the elements of the line bundle. Okay, I just want to make a comment that here, J, we have for each one of these spaces, Zi or Zk, say, we get a different moment map. It's kind of a new moment map, but it's just constructed from J0 and the toric moment map. Okay, so it's not that complicated. Okay, so that's kind of geometrically how the monodal structure is encoded. One way of saying this is that you can kind of package all of the spaces Z together, and it gives you a big holomorphic symplectic groupoid. It's kind of it's kind of Z graded, and it's equipped with a multiplicative prequantization. So it's holomorphic prequantization, but it has like a product structure, which is what this cocycle gives you. Okay, so that's sort of that's basically how we get these branes and what's going on with the tensor product. So the last thing I need to say is, well, we want to compute these homomorphism spaces. And remember how we did it in the Kähler case, is that what we did is that we had to take a holomorphic polarization of the holomorphic symplectic manifold, and we looked at the foliated at the flat sections along the foliation, and that's how we were looking at the flat sections along the fibers that actually intersect this this L here. So we want to do that in this case, but there is one problem, is that this original polarization, it might not be adapted to the tensor product structure. So that's kind of one difficulty, is that you need to choose, in order to kind of implement this construction, you need to choose a polarization which is well behaved with respect to the tensor product structure. So in this case, we're not going to use the fibers. We're going to use a different holomorphic polarization, and it's going to be given by exactly by these moment maps, J. So we need a holomorphic polarization compatible with the product structure. And this is given by the holomorphic moment maps J from these spaces Zi to C. Okay, so remember the spaces of homomorphisms from L to BI, it was supposed to be the flat sections of view I di along fibers of ji that intersect L. So let me give a picture of what's going on down here. So here's our space. Here is L. And I'll just draw the space filling brane like this. And we have this map J, which goes to C to the N. And it has these fibers, which I'll write in green. Okay, so there's two things to note. This polarization it behaves very differently than the fibers of the projection map. So here's two things to note is that not all fibers admit flat sections. So we have a quantization condition. So only some of these fibers actually admit flat sections. The problem is that there is monodromy obstructing it in general. So the ones that do admit flat sections are the so-called Bohr-Sommerfeld leaves. And these correspond, they're in one-to-one correspondence with the lattice points. Z to the N inside of C to the N. So that's kind of the first thing that's happening. Kind of some special lattice points. The second key thing is that not all fibers intersect L. And for this, what you find is that a fiber, J inverse of K, it intersects L if and only if K is in the Delzant polytope for K omega. Because remember, we have we're dealing with the toric variety, so we actually have this moment polytope. So only the lattice points that are actually lying in the moment polytope correspond to fibers that intersect L. Okay, so in this case, what we get when we compute the quantization, homomorphisms from L into, say, B tensor K. So that's the direct sum of over BS leaves intersecting L of the global section over the leaf of U, the global sections that are flat. And what we get basically is a decomposition over, over the points inside of the Delzant polytope intersect the lattice points. And this is actually canonically isomorphic to the global sections of the line bundle. Again, it's actually giving us the weight space decomposition. Okay, so we kind of get sort of an independence of polarization. Well, actually, the geometric quantization of this holomorphic symplectic manifold, it does depend on the choice of polarization. But if you impose the fact that they are only taking these Lagrangians that intersect L, then it kind of restores the invariance. Okay, so if we do this, let me just state this as the final theorem to finish. So this is what we show in the paper. So we kind of carefully go through this construction, and we can compute what the algebra is, and the algebra, which I'll call, say, AC, is given by kind of canonically isomorphic to as a vector space to the homogeneous coordinate ring. But the product is deformed with deformed product. So F times G is going to be equal to exponential of IC of W1, W2 over 4 pi times F tensor G, where W1 and W2, these are elements in the dual space of the torus. These are the weights of F and G respectively. So we find kind of like a quantum torus, but kind of compactified to a toric variety. Okay, so I think I'll end there.
Okay, thanks, Francis. We've had a lot of questions. Are there more?
Yeah, so at the beginning of your talk, you said that this twisted homogeneous coordinate ring is the deformation quantization. And like in this case, I see that that's true, but that's not like a theorem. That's not true in general. There's no like direct link between that and formality, say.
What do you mean?
Just at the beginning of your talk, when you wrote down the twisted homogeneous coordinate ring, you said that this was the deformation quantization.
Right. So this is what we would expect. I mean, because we can't actually implement the procedure for if you just give a Poisson structure. I don't know how to do it, but that's what we're aiming to get. But like in particular, what we would get if we could do it is we would get an actual convergent deformation. It wouldn't just be formal in this case.
Right.
Yeah, but it should correspond to, I mean, that's sort of what this original observation was telling us, that the deformations of the GC structure and the deformations of the category of coherent sheaves, they're kind of given by the same thing. So we should expect that the deformation of the homogeneous coordinate ring given in this way, it should be the deformation quantization.
Right. It's just not formal here, which is nice.
Yeah, so that's one of the things that we want to do, is for more complicated Poisson structures, find kind of a more geometric way of constructing a lot of these interesting algebras that people find.
Okay. Thanks.
Yeah, one question. If you consider the formations of a standard complex structure by this GRB part, do you know how to implement this program?
I have not thought about it. Maybe it'd be related to these Azumaya algebras. I'm not sure. Yeah, sorry, I haven't thought about this at all.
earlier you defined this theta of xy acting on f and g, and you called it a cocycle. Is this like a Hawkshield cocycle in some sense, or?
It's it's more of like it's more of like it's a groupoid cocycle. So sort of like how groups have group cohomology. So you can define a group cocycle. It's similar to that.
Okay.
But yeah, it's a good question. That it should be related possibly to a Hawkshield, or like whatever you get for deforming algebras. There should be a relationship, but I'm not sure about what the precise relationship is. But no, it's more like it's a groupoid cocycle.
Okay, thanks.
All right. Well, yeah, if there's no other questions, let's thank Francis again for a very nice talk. And